Welcome to the GCSE Statistics Higher Session 10. This session is focused on data from tables and the binomial theorem and consists of three subsections: extracting data from a table, simulations, and the binomial theory. Interpreting data from a table. You need to be able to identify basic information in a large data table. Highlighters here will be useful. Once you've identified information, you need to be able to compare two or more populations. Following this, you need to be able to describe a trend. This will simply be saying something is increasing, decreasing, or staying the same. If the data is presented in percentages, it should add up to 100%. If it doesn't and adds up to 99% or 101, you may be asked why. The simple reason for this is rounding. Once you've identified data from the table, you may be asked to comment on this data. And to do this, you need to relate the data to the real world. So at this point, you need to use your general knowledge of things happening as to why the data might be showing an increase, a decrease, or staying the same. Example number 1. The table here shows a part of a larger table that shows the examination achievements by pupils in 2001 and 2002. Here on the left-hand side, we have a number of regions. And across the top here, we have the percentage achieving different classifications of GCSEs. Here on the left-hand side, we have 5 or more grades, A star to C, 1 to 4 grades, D to G grades only, and the percentage of pupils achieving no GCSE grades. Here we have the total in thousands. So our first question is to identify what percentage of pupils in the Northwest got 5 or more A star to C grades. So we're looking here at the Northwest from the question here. We're then looking at 5 or more A star to C. So this is the column we're focusing on. The value here is 48. So the percentage of students achieving 5 or more A stars to C in the Northwest is equal to 48%. We're then asked to write down the total number of pupils in the United Kingdom in the last year of compulsory education in 2001 to 2008. So here now we're looking for the total number, not the percentage. So we're going to be looking here. We're looking at United Kingdom, and we can see here this is our totals across and our value here in thousands. Identifying from the table here, the total 729,700. So this number here, we must multiply by 1,000 because of the percentage, the fact that in the data table, the figures quoted are in thousands. We're then asked to identify which region shown in the table had the lowest percentage of pupils with no graded GCSEs. So if we're looking for the lowest percentage of students with no graded GCSEs. Let's take a look here. So the column we're interested in is here, no graded GCSEs. We're looking at the regions, so starting here, we're looking for the lowest percentage. And we can see here that the lowest number from the table is right here at 4.6. This is the lowest percentage, and it corresponds with the region East. We're then told that the following statement is wrong. This is not correct. 19.5% of pupils getting grades D to G only take their GCSE exam in London. Okay, let's take a look here. We're looking at our table here with the grades. I can identify here with the blue, grades D to G, and we're interested in London. So we take a look here and we see London says that 19.5. The number here corresponds here, and we're looking at the column D to G as we are. But this statement is incorrect. We need to change the statement because here we say that 19.5% of pupils getting D to G only take their GCSE exams in London, whereas 19.5% of pupils who take their GCSEs in London get D to G. So recorrecting this, we need to say that 19.5% of pupils who take. So the first part will stay, pupils who take their GCSEs in London get D to G. Looking now at example number 2. This table below is part of a larger table that shows the percentage of male and female pupils achieving GCSEs in the United Kingdom in the same year. We're told that the percentage of male pupils do not add up to 100%. So if we see here, we have our percentages, and we add these percentages up, they come to 99.9%. Why not 100? This reason will be because of rounding. Each one of these would have been rounding, and we would have lost 0.1%. Example number 3. The table gives the life expectancy at birth in years for men and women born in 1960, 1970, 1980, and 1989. We can see here split men and women. A woman was born in Ireland, this is here, in 1980. So it's a woman born here in 1980. Write down her life expectancy at birth. So we're looking here for Ireland, and we'll go down across to find the corresponding value, 75.6. So our answer for A is 75.6 years, extracting the information directly from the table. We're then asked to work out the increase in life expectancy at birth from 1960 to 1989 for men born in the UK. So let's focus in now, men in the UK. We're looking at the year 1960 and we're looking how much it's increased to the year 1989. So these are the two figures that we're interested in. So we're looking to see the increase. What's the increase between here and here? What must we add? What's the difference? We can take our life expectancy in 1989 and subtract the life expectancy in 1960, which gives us an increase of 4.5 years. So between these 2 years, 1960 and 1989, the life expectancy at birth has increased by 4.5 years for men in the United Kingdom. We're then told that men and women born in the UK in 1989, so we're looking at UK here, 1989, this is men, and here is women. And we're told that they had different life expectancies. We can see here by the different numbers in the table. And we're asked to work out the difference. Exactly as we did before, finding the difference of these two numbers, we must also find the difference of these two numbers by subtracting. So 78.1 subtract 72.4 gives us the difference of 5.7 years. The next question is about trend. We're asked to comment for 1 mark only, the way life expectancy at birth in these countries, all the countries here listed, has changed from 1960 to 1989. So we're going to have to make a general comment. We can see here both in the men and women, we can see each time comparing, doesn't matter which country, the life expectancy has increased. All of the values in the column for 1989 are larger than the values in the column for 1960. So life expectancy has increased. We're then asked to compare the life expectancy at birth for men and women. Again, there's only 1 mark available for this, so we're going to have to make one statement in relation to the life expectancy at birth for men and women. So no country specified, no year has specified. But let's take some comparisons here. If we look at Belgium here, men, 67.7. Look here, same year, women, same country, higher. Let's take some more here, 1970, Italy. We can see here the value for women, the corresponding value for men, lower. Netherlands, let's have a look here in 1989, compared with 1989 here. We can see comparing all of the values, women have a higher life expectancy than men. So one general statement comparing men and women, that women have a higher life expectancy than men. Stimulation. It may not be possible to carry out an experiment in order to estimate the probability of an event happening. This may be because it's too complex or it's just not desired. In such cases, you can stimulate the problem, and this is what this part of the session is about. Stimulations are quick and cheap, easily altered and repeatable. There are several ways of introducing randomness into a stimulation. We can use coins, dice, random numbers from a calculator or from the random number tables. You need to be able to create a stimulation rule, and you need to be able to apply this rule. So let's take a look at what creating a stimulation rule involves. We have numbers allocated in proportion to probability. You need to be able to do this with both 1-digit numbers and 2-digit numbers. And realise that when proportions are not exact, and we have a fractional probability, for example 1/3, we must reject and redraw for some numbers. Again, when we're applying the stimulation rule, we just replace the numbers with their real values. Let's take a look at an example, and we're going to focus here on creating and applying a stimulation rule. There are 2 types of customers who use the shop at a service station. 70% buy fuel and the other 30% do not. There's only 1 till in operation. We're asked to give an efficient rule using 1-digit random numbers to stimulate the type of customer arriving at the service station. So 1-digit random numbers are from 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9 inclusive. So on a previous slide here, where we were talking about 1-digit numbers 0 to 9 inclusive, these are the values here. So there's 10 numbers. We have here the proportion who buy fuel. 70% of the people buy fuel. We have 10 numbers. 70% is going to be represented by the first 7 numbers. 7 over 10. And this is for them that buy fuel. And here are remaining 3 numbers, 30%, do not buy fuel. So here we could have a simulation from 0 to 6 for fuel and 7 to 9 for no fuel. This here is stating a simulation rule, given the probabilities in the question. The table here shows the distribution of time taken at the till by customers who are buying fuel. Here we have different times and a probability associated with each time. We again are specifying an efficient rule for using one-digit random numbers again. So we'll write out our numbers 0, 1, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we have 10 numbers. We can see here that 3 out of 10 take 1 minute. So here, these three values, 1. So you might want to create a table here saying time 1, 0 to 2. Here, we need to change this to a denominator of 10 to identify that we need 4 of the next numbers, 1, 2, 3, 4. This here is for 1.5. So a time of 1.5 minutes can be stimulated by the random numbers 3 to 6. Here again, converting this to an equivalent fraction, we have 2 over 10. These are our next two numbers here. For time 2, 7 to 8. And lastly here, for time 2.5, 1 over 10, 1/10, the last number here for 9. Example number 6. This example involves using a 2-digit random number. So I'm not going to write out all the numbers, but we will go from 0 all the way inclusively to 99. This is the 2-digit random numbers. So here we're given a distribution of time taken at the till by customers who are not buying fuel. We can see here that we have, using a 2-digit random numbers, we have 100 numbers. Dividing through by 7 here, we get 14 remainder 2. This means that a probability for 1 over 7 is going to be equal to 14 of the numbers. So here, this is an example, as I mentioned earlier, that we have what we have here, that a proportion is not exact. Therefore, we must reject 2 of the numbers. So we are not going to need 2 of the numbers. So we will only use up until 97. So we reject 2 numbers, the 2 at the end, we don't need 98 and 99. So looking here now, we need to set up a simulation for random numbers for 1. So time for 1. This has a probability of 1 over 7. So we're going to take the first 14 numbers. So we will go from 0 to 13. 0 to 13 includes 14 numbers because the 0 counts as a number. Time of 1.5 is 2/7. So this time we're going to take on 28 numbers. So we must go from 14 up to 41. Time of 2, same thing, 28 numbers, from 42 to 69. Next, we're back to 1/7, which is 14. So we will go for 2.5 from 70 up to 83. And then lastly here, for time taken being 3 minutes, we are looking from 84 to 97. Our 2 numbers here that we are rejecting, we state that they are rejecting and not part of the rule here. In example 7, we have been given the rule and we are going to apply it. We're told that 10 customers all arrive, none of whom are buying fuel. Using the rule below here, we have our times, and here we have the rule. This was the rule we just created on the previous example. But this time we're asked to work out the mean time taken. So we have here 10 random numbers generated. These are here corresponding to our 10 random customers. And we're going to stimulate here to find the mean time taken. So our first person has a random number of 55. Where do they fall in the rule? 55 is between 42 and 69, so our first customer has a time of 2. 06 is 1. 80 is in here, 2.5. Cross these off as we consider them. 67 is here in 2. 91 is here, 3. 64 is 2. 79, 2.5. 52 is 2. 33 is 1.5. And lastly here, 89 is in the last category, 3 minutes. To be able to find the mean, like we would with any set of numbers, we must add up each of these times. And then divide by how many times there are. In this case, we have 10 random numbers. We are dividing through by 10. So our total is 21.5 divided by 10 gives us the average time of 2.15 minutes. So here, using our probabilities and our rule here, we can then stimulate a situation where we have 10 customers, 10 potential customers arriving, seeing where they fall given our rule, and then we can calculate the mean time taken. The binomial theorem. Here we have only 2 outcomes, success or failure. Bi here is in our clue with the name bi meaning 2. 2 outcomes. Success is denoted by P. Failure is denoted by Q. You must know and recognize these 2 letters in the context of the binomial theorem. Here we can see that the probability of success plus the probability of failure is equal to 1. The probabilities add up to 1. It's like the probability of something happening and the probability of something not happening adds up to 1. You need to be able to calculate probabilities, the likely chance of something happening. And the binomial expansion assigns probabilities to each compound outcome. So by using the binomial expansion, it will tell us the probability of hitting something 3 times, 2 times, 1 times, 0 times, depending on how many are in the expansion, what the power of the expansion is. You need to know the expansion for P add Q, success plus failure squared. However, all of the other expansions to the power 3, 4, and 5 will be given to you in the question. Here, the expansion for P plus Q squared is like expanding a double bracket. So we will have P squared plus 2PQ plus Q squared. The best way to remember which probability goes with each outcome is to match up the powers of P with the number of successes. We're having a look at how one of these works in one moment. The key assumption is that events are independent. The probability of one event is not affected by the probability of the other event. Example number 8. Barry has 2 fair dice. Each dice has 6 sides. Barry rolls both dice. He rolls both dice. He adds the numbers on the top of the 2 dice to get his total score. So first off, we're asked to write down all the ways that he can score a 7. He can get a 1 and a 6, a 2 and a 5, a 3 and a 4. He can also get a 4 and a 3, a 5 and a 2, a 6 and a 1, so the other way round. So we want to write down all the ways. Here, there are 6 different ways. You need to state these 6 combinations. We're asked to write the probability that he scores a 7. Well, it happens 6 times out of possible outcomes of 36. You can see that by doing a table with 1, 2, 3, 4, 5, 6 across here. 1, 2, 3, 4, 5, and 6. So there are 36 different combinations. So here, the probability of scoring a 7 simplifies to 1 over 6. We're then told that Barry rolls both dice together 80 times, and we're asked to estimate how many times he scores a 7. So to estimate this, we take the probability of scoring a 7, 1 over 6, times by 80. And this round's estimate is to 13, to the nearest whole number. Okay, so we're now going to move on to the binomial theorem part. We're told that Megan throws darts at a target. She can hit a target with 7 out of 9 throws. So immediately, the probability of success is 7 over 9. The probability of failure, Q, will therefore be 2 out of 9. Remember, these two must add up to 1. We're told that she throws 3 darts. We are then given the binomial expansion for the 3 here. She throws 3 darts, therefore the binomial expansion is for 3. This is where the 3 here is from. And we're asked to work out the probability that she hits the target exactly twice. So P is squared if it happens twice. So looking at the expansion here, this means she hits the target 3 times. Here, P is squared. She hits the target twice and misses once. This one hits the target once, misses twice. Here we have Q to the power 3. This means misses the target 3 times. So the one that we're interested hits the target exactly twice is this part of the binomial expansion. So we're going to substitute in our probabilities to find out here the probability of hitting the target twice. 3 multiplied by the probability of Q, 7 over 9, squared, multiplied by the probability of failure, not hitting, missing, 2 over 9. Multiplying this out gives us the probability of 98 over 243. We're then asked a very standard question. In order to assume a binomial distribution, what do you have to assume about the probability of hitting a target with each of the 3 darts? Really important, simply writing the word independent. And what that means is that each dart has the same chance of hitting the target. So if you hit the target, your probability of hitting a target again is exactly the same, remains unchanged. However, we are then told that the assumption may not be realistic and asked to write down one reason why. Well, if you're playing darts and you have a dartboard and the target is this little space here in the middle and you throw a dart and it hits here. And then you throw another one. Is the probability actually the same? Well, maybe not. Maybe the space here for the target to hit has decreased. So actually, this assumption may not be realistic because the target space has decreased. Example number 9. Gordon is going to throw 5 stones in turn at the target. Gordon can hit the target, success, with a probability of 0.8. So P for success, 0.8. With any one of these 5 stones, independent. If the probability of success is 0.8, therefore the probability of failure is 0.2. Why? They must add up to 1. We then ask to name the probability distribution that models the number of times he will hit the target in the 5 throws. This here is a binomial distribution. We're asked to work out the probability that we'll hit the target with only one of the 5 stones. So here we have 5 stones, therefore we have a binomial expansion for 5. We're looking for hitting the target only once. So P is just P to the power 1, which is the same as P. If he hits only once, Q must be to the power 4, because if he hits it once only, the other 4 times he misses. So, which part of the binomial expansion are we interested in? Hitting once, P, missing 4 times. This part here. So we have 5 multiplied by 0.8 multiplied by 0.2 to the power 4, which gives us the probability of 0.0064, the probability of hitting the target with only one of the 5 stones. We're then asked to work out the most likely number of times he will hit the target. So once again, we're going to use the same binomial distribution. So what's the most likely? Well, we've already worked out the probability for hitting the target once. Let's work out the probability of hitting the target twice. Hitting the target twice is P squared. So here we are looking at this part. Substituting in our values, we will get a probability of multiplying these together. So we must multiply 10 multiplied by 8.5 squared. So we have 10 here, multiplied by 8.5 squared, which is 0.64, multiplied by 0.3 to the power 3, which gives us 0.027. Multiplying this out gives us our probability of 0.005 here. What about the probability of hitting the target 3 times? 3 times, we are looking here at P3. So this is what we are going to calculate. 10, so you see, 10 multiplied by the probability of hitting the target 0.8, 3 times the probability of 0.2 not hitting the target 2 times. Here we have our probability of 0.05. Sorry, 3 times we're hitting here, not 0.05. We have our probability of 0.2. For 4 times, here we are interested in this part of the binomial expansion. Substituting in our values, we have the probability being equal to 0.41. And lastly, for 5 times, hitting the target 5 times. Hitting the target 5 times is here, P to the power 5. No failures. So we are simply multiplying 0.8 to the power 5. So 0.8 to the power 5 is 0.33 rounded. We're asked what is the most likely? It's the one with the highest probability, which in this case we can see here is 4 times. So this is the most likely number of times he will hit the target, 4 times. It's now time for you to complete some questions. Press pause on the video and complete the question booklet. Once you have completed as many questions as possible, come back to the video, press play, and we will be going through the questions together. Question number 1. The table shows the numbers of casualties from road accidents in thousands involving illegal alcohol levels in Northern Ireland in the years 1986 to 2000. We're asked to write down for section A the total casualties in 1989. So A, the total casualties, we're looking at this column, and the year we're looking for 1989. Here, reading across in our table, this here is our value. Total number, 22.81 thousand. We're then told that the total number of injuries in 1996 found by adding together fatal, serious and slight, so from here 1996, adding fatal, serious and slight injuries columns comes to 17.66 thousand. The number of casualties in total column here is 17.67. Give a reason for this difference. Why do these two not match up? This is a standard answer, and it is to do with the way that the numbers have been rounded. Reason, rounding. In part C, we're asked to describe the trend in the number of fatal injuries in the years 1986 here to 2001. So we're looking here and we're looking at fatal injuries. So the numbers here, what do we notice about the numbers? We can see that they are decreasing. The numbers here, year on year, are falling. So the trend is decreasing. And then in the second part, we're asked to focus on the years 1993 to the year 2000. So here, 1993, here to the year 2000. What is happening here to the number of fatal injuries? We can see here, we start at 0.57, we drop slightly, we go up, we go back to where we were, and then we fall, and then back up again. So an acceptable answer for part 2 would speak about this trend in a number of ways. It's relatively level. Another word to describe that would be flat, or stays the same. There are some small fluctuations which you might want to talk about. It going up slightly to 1996 and then falling again. So a slight increase followed by a small decrease, and then at the end again it goes up again. So it's relatively flat, stays the same, only small fluctuations. Question number 2. The table shows information about the number of energy units supplied in Great Britain. Here we have the years, here we have the total, and then the different energy type, different number of energy units supplied, and then net imports here. We're asked first, part A, how many units of nuclear supply in, how much units of energy did nuclear supply in 1998? So we're looking here at the row for 1998, and we're looking for nuclear. So this is the value we are reading from the table, 23.39 units. In part B, we're asked which source supplied the greatest number of energy units. In 2005, taking a look here at the year 2005, which of these numbers is the greatest? We can see here 76 is the largest number, 0.6, so petroleum. Whereas in 2003, the year here, the second year we're asked to compare against, here in 2003, coal, petroleum, 75.7, natural gas, higher than the nuclear and higher than natural flow hydro. So in 2003, the highest is now natural gas. C. Describe the trend in the net imports of energy units between the years 2000 and 2003. So we're looking here, net imports 2000 to 2003. Looking here at the numbers starting at 1.22, what's happening each year? Decreasing. So the number of net imports of energy has been decreasing between the 2 years 2000 and 2003. Question number 3. The table shows information about births in England and Wales for the years 1995 to 2002. We have here our years, and here we have different categories measured here in the table. A. We're asked how many births were in the year 2000. So we're looking for the year 2000 here, and we're looking about the number of births. So here, the number of births in the corresponding row 2002, the number of births we have is 604,441. Then in part B, we're asked to describe the trend in the mean age of mothers at childbirth between the years 1995 and 2000. So all the way from here, 1995 to 2002. We're looking at the mean age of mothers. So this here for part B is what we are looking at. The mean age of mothers. Starting here in 1995, at 28.5, we can see each year it gradually increasing. So what's happening to the trend? It is increasing. Then for part C. In part C, we're told that every year between 1995 and 2002, there were more male births than female births. More male than female. How does the table show it? We can see, looking at this column here, which is the data for the male births per 1,000 female births. So for every 1,000 female, there is 1,051 males. So here we can see there are always more than 1,000 male births for every 1,000 female. Here, all of the numbers are above 1,000. And this shows that more males than females are born. Why? Because looking at this column, there are always more than 1,000 male births for every 1,000 female births. So identifying this column is important when giving your reason for the answer to part C. Looking now at D. From the table, what can you infer about the trend in the percentage of births to mothers born in the UK? So we're now interested in this final column of our table. we can see here that our numbers are increasing. This means that the percentage of births to mothers not born in the UK is increasing. So, if the percentage of births to mothers not born in the UK is increasing, we can see there that the percentage of births to mothers born in the UK is decreasing, as the percentage of births of mothers not born in the UK is increasing. So let's just write this down. The increasing births to mothers not born in the UK means the percentage of mothers, the percentage of births to mothers, I should put that there, to mothers born in the UK is decreasing. So as one is falling, the other one is decreasing. Question number 4. Peter is a supporter of Valley United Football Club. Valley United have played 40 games. The table shows the number of games won, lost, drawn. Peter wants to simulate the results for Valley United's next 10 games. He uses random numbers between 0 and 99. The table below shows the numbers he gives to each result. So this here is the rule that he's created. Explain why he gives the numbers 0, 0 to 49 to the number of games won. Let's look at the information provided here about the number of games won. The number of games won was 20 out of the previous 40, which is 50%. And 0 to 49 is 50% of the possible numbers. Therefore, that's why these numbers have been chosen here for the one result. Peter uses the following random numbers to simulate the results of the 10 games. We need to complete the table to show the results of the simulation. So let's take these numbers and find out which category they fall into. First off, the first category for 1 is all numbers between 0 and 49. We have 6, 1, and we have 33. So there are two numbers between 0, 0 and 49. Lost, we have 55, 80, 67, 64, 79, and 52. Altogether, 6 numbers. And our remaining 2 numbers here are in this column for drawn. We're asked, how does Peter's simulated result compare with the expectation based on the first 40 games? Well, it doesn't look very good because we've just worked out that on the first 40 games, the win was 50% in the first 40 games. Now looking here at the simulation, we have only 20%. 20 out of the 10 here, sorry, 2 out of the 10 here, 20%. 1 in the simulation. So actually, the simulated result does not compare very well to the result or the expectation based on the first 40 games. How could he improve this? With all of these types of questions, you need to increase the number of times the experiment is carried out or the simulation is carried out. So increase simulation. So he needs to repeat it more times. Increasing the frequency of doing it will increase the accuracy. Question number 5. John is going on a 4-day holiday to Costa Packet. The travel brochure says that on an average, 5 out of 7 days are sunny. 5 out of 7 days are sunny. That is the probability of a success. This is the success. So therefore we know the failure, the days it's not sunny, will be 2 out of 7. Each day's weather is independent of the weather on the preceding days. Independent. Key assumption for the binomial distribution. We're asked what are the two values of n, that's the number, and p that you will need to use in this probability distribution. N is how many days. Here we're told John is going on a 5-day holiday. The value of P is the success, the probability of success, the probability it is sunny, 5 over 7. We're then asked to calculate the probability that John has 2 or less sunny days on his holiday. So looking here at the binomial expansion, we're looking 2 or less. So P equaling to 2 here, 1 here, nothing here. So this is the part of the binomial expansion that we are interested in. So substituting in here, we will have 10, 5 over 7 squared, 2 over 7 to the power cube, the third power, at showing all your steps and using your calculator, you will get a probability of 0.1447. What is the most likely number of days, sunny days, that John will get on his holiday? So he could get 5 days, all the days being sunny. And we can see here, the binomial expansion, that's when the probability here, 5 over 7, straight to the power 5, which is 0.19. The probability of getting 4 days is the next part of the binomial expansion, 0.37. The probability of getting 3 days sun on the holiday is 0.3. Now there's no point in working out any of the others for 2 or 1 because we can see here that these probabilities, adding them up, already add up to 0.6, 0.7 over 0.8. So the remaining 2 probabilities will be less than these probabilities here. And we can see that the largest probability, the most likely outcome, is this with the highest probability, 4 days of sun. Question number 5. A company runs holiday tours. In 2002, 400 people made provisional bookings. Of these, 320 went on to confirm the booking. What's the probability of the booking being successful, then confirming? 320 out of the 400, which is the equivalent of 4 over 5, or expressed as a decimal, 0.8. In 2006, one person makes a provisional booking. Write down an estimate of the probability that this person will go on to confirm the booking. We've just calculated that here. It's the probability that the person will make the booking. We're then asked to estimate the probability that the person will not go on to make the booking. Making the booking and not making the booking must add up to 1. So the probability of not making the booking, confirming, must be 0.2. So that these 2 values for the probability add up to 1. We're then told that the tour company had just 4 people, n equals 4, who made provisional bookings. Calculate the probability that exactly 3 of these people will go on to confirm their bookings. Exactly 3. Probability 3. So we're looking for success, that's our P, being 3. And we can see this is the term we are interested in. So 4 times 0.8, that's the probability of success that they do confirm, to the power 3 multiplied by 0.2. You can express your answer as a fraction or indeed as a decimal. So this here is a probability that exactly 3 of these people will go on to confirm their booking. For these 4 provisional bookings, which are the 2 most likely numbers of people who go on to confirm their bookings? So here we have 4 people. All 4 could confirm their bookings. 3 of them could confirm their bookings. 2 of them could confirm their bookings. 1 could confirm their bookings. And 0 could confirm their bookings. You need to calculate the probability for each one of these and identify the 2 most likely. We've already worked out the probability for 3 of them confirming in the previous question, 0.41. Probability of 4 is 0.4096, just this part. This is the probability for 4. This is the probability for 3. This probability for 2, substituting in your values, you will get a probability of 0.1536. This is for 1, 0.0256. And lastly, here, for no one, all of them not confirming, probability of 0.0016. So which are the 2 most likely options that will happen, most likely numbers? We're going to be looking for our highest probabilities. We can see it's these 2. It's most likely that either 4 or 3 of the people confirm their bookings. Question number 7. The probability that an electrical component is faulty is 0.5. Write down the probability that the electrical component is not faulty. 0.95. We find that by subtracting one from the other. So here we're looking at the probability that for success, that it's successful if the component does not have a fault. So the probability for success not having a fault, 0.95. Defining this, no fault. And that can be classified as the success. Q is equal to 0.05, and this means that the electrical component does have a fault. And equal size samples of the electrical components are selected at random. Give the name of the distribution that can be used to model the number of faulty electrical components in these samples. Binomial. There are 4 electrical components in a sample. N is equal to 4. Calculate the probability that exactly 3 of the electrical components are not faulty. Okay, not faulty. So we need our P to be to the power 3. So we're looking here at this part of the binomial expansion. So 3 are not faulty. 4 multiplied by 0.95 to the power 3 multiplied by 0.05, which gives us our probability of 0.171. We're then asked to calculate the probability that more than one of the electrical components is faulty. More than one is faulty. So let's take a look at our binomial expansion here. The first part, p to the power 4, means that all 4 have no fault. So not this one. Here we have 4 times p to the 3 multiplied by q. Q is just 1. That means 1 fault. We're looking for more than one. So the part that we're interested in is here, where there's 2 faults, here, where there's 3 faults, and here, where there are 4 faults. So substituting in all the values here, again, we are looking at 6, 0.95 squared, multiplied by 0.05 squared. Add 4 multiplied by 0.95 multiplied by 0.05 to the power 3. Add Q again, 0.05 to the power 4. Adding all of this up and giving your answer correct 3 decimal places, 0.014. This is the probability that more than one, doesn't include one, more than one of the electrical components is faulty, either 2, 3, or 4. Adding them all up gives us a total probability. We've now come to the end of session 10. Please review the list of topics shown here on the screen and replay the video for any section that you would like to revise again.